Hello, this is video number 10 on my single variable calculus 2. In this video, we're going to talk about general exponentials and logarithms. So start with a real number a that is positive and is not equal to 1. Then we can look at the graph of a to the power of x. If a is greater than 1, then we would get this graph. So at x equals 0, it passes through 0, 1. And as x goes to infinity, a to the power of x goes to infinity. As x goes to negative infinity, a to the power of x goes to 0. So this is the graph of a to the power of x when a is more than 1. Now when a is less than 1 and positive, this is the graph of a to the power of x. So this is y equals a to the power of x when a is less than 1. And for all of these, we are assuming that a is positive. Now, if a is equal to 1, we would get this graph. So this is y equals 1 to the x, which is just always 1. So clearly this function 1 to the power of x is not 1 to 1. So there is no inverse for this function. But when a is between 0 and 1 or more than 1, a to the power of x is either strictly increasing or strictly decreasing. In the case that a is greater than 1, the function is strictly increasing, and in the case that a is between 0 and 1, a to the power of x is strictly decreasing. What does that mean? It means it has an inverse. So both of the inverses are called log. This is log of x base a. So what's the relation between log and exponential? They are inverse functions, which means log of x base a is equal to y precisely when a to the y is equal to x. Note that x must be positive, a must be positive, but y could be any real number, and a cannot be 1. These are the three restrictions. A and x must be positive, and a cannot be 1. One of the really useful formulas from pre-calculus that we're going to be using here is the change of base formula. Log of x base a is natural log x over natural log a. This really helps us in integration and differentiation of logs in other bases. So let's do a few examples on differentiation and a few examples on integration. The first example involving 3 parts is differentiate each of the following. So we're going to go over the solution of this one. So we want to differentiate this. So we're going to turn this one into log base e, and then we're going to differentiate. So how do we turn it into log base e? Well, we are going to use the change of base formula. So this would be derivative of natural log of x squared plus 1 over natural log of 5. But note that natural log of 5 is a constant, so we can take it out. So this would be 1 over natural log of 5 derivative of natural log of x squared plus 1. Now, natural log of x squared plus 1 is easy to differentiate. We'll have to use 1 over x squared plus 1 times the derivative of inside. So 1 over natural log of 5, 1 over x squared plus 1 times 2x. So in other words, we're using the chain rule here. So this would be 2x over natural log of 5 times x squared plus 1. Okay, so next example, we want to evaluate the derivative of log of cosine of x in base 3x. So again, we're going to use the change of base formula. So d dx log of cosine of x base 3x would be derivative of natural log of cosine of x divided by natural log of 3x. So this one we have to use the quotient rule. Bottom is natural log of 3x squared. Top is derivative of numerator. This is 1 over cosine of x times negative sine of x times denominator, natural log of 3x, minus derivative of denominator, 1 over 3x, times derivative of inside, which is 3, times numerator, which is natural log of cosine of x. So this is the answer to the derivative, and now we're going to take this and we're going to take the common denominator and we're going to simplify this. So the common denominator is cosine of x times, so if you Look at this one. The 3 cancels, so times x, and then natural log of 3x squared. In other words, I'm multiplying both numerator and denominator by x times cosine of x. So this becomes minus x sine x. Then I have natural log of 3x, and then minus cosine of x times natural log of cosine of x. So this is the derivative of the log that we were given. Next part is differentiating 7 to the power of tangent of x. So for that, we can use logarithmic differentiation. So y equals 7 to the power of tan of x. We are going to take the natural log of both sides. This would be natural log of tangent of x, or rather tangent of x, because the exponent comes to the front, times natural log of 7. Now we're going to differentiate, so this is 1 over y times y prime. Now, derivative of tangent is secant squared, and natural log of 7 is just constant, so we don't need to worry about that. So we'll just leave it as it is. So that tells us that y prime is equal to y times secant squared x times natural log of 7, which tells us that y prime is 7 to the power of tan of x times secant squared x times natural log of 7. So this is the answer to the differentiation that they gave us. So in general, if you want to find the derivative of a to the power of x, we can use logarithmic differentiation. This formula is pretty simple, so it is, I would say, worth remembering. So we write down y equals a to the power of x. We take the natural log of both sides. We differentiate. So we get 1 over y times y prime equals natural log of a. Multiply by y. You get y prime equals y natural log of a, which means derivative of a to the power of x is a to the power of x times natural log of a. So that means derivative of a to the power of x over natural log of a is a to the power of x. If we divide both sides by natural log and put it inside the derivative, because any constant can be taken out of differentiation. So that means the integral of that is this one. So integral of a to the power of x is a to the power of x over natural log of a plus c. So now let's do a couple of integration problems. Evaluate each of the following. Integral of log of x base 2 over x. Well, we're going to again do the change of base formula. So integral of natural log of x over natural log of 2 times x dx. So for this, we're going to use a u substitution. Natural log of x du becomes 1 over x dx. So now 1 over natural log of 2 is a constant, so we can take it out of the integral, and 1 over x dx is du, and natural log of x is u. So this would be 1 over natural log of 2, and then we have u squared over 2, and then plus c. So this would be natural log of x squared over 2 natural log of 2 plus c. The second part is asking us to evaluate the integral from 0 to 1 of 2 to the power of x cubed times x squared. So when I look at this integral, I see the derivative of x cubed is 3x squared, which is in fact present inside the integrand. So it makes sense to use a u substitution for x cubed. We get du equals 3x squared dx. X squared dx becomes 1/3 du. So we are going to change this to du. So this would be 2 to the u. X squared dx is 1/3 du. Now we need to look at the limits of integration. X0 gives us u equals 0 cubed, which is also 0. X equals 1 gives us u equals 1 cubed, which is also 1. So this is the integral from 0 to 1. And this is 1/3 the integral 2 to the u du. Now, what is the integral of 2 to the u? Well, we just talked about that. That is 2 to the u over natural log of 2. And that should be evaluated from 0 to 1. Now we're going to plug in the values. We get 2 over 3 natural log of 2 when we plug in u equals 1 minus 2 to the 0, which is 1 over 3 natural log of 2. So that gives us 1 over 3 natural log of 2. So that is the answer to the question. Okay, one last example and then we summarize. Consider the region R that lies between the curves y equals 2 to the power of x and y equals 1/3 to the power of x and line x equals 1. So the first thing is sketch the graph here. So we have y equals 2 to the power of x, y equals 1/3 to the power of x, and x equals 1. So this is our region. And we are rotating this region about the line y equals -1. So y equals -1 is here. And when we rotate this, we're going to have to reflect this about the line y equals -1. So 1 comes to, origin comes here, -2. 1 comes to -3. And then we can draw this one. So we have the reflection of the bottom one. This bottom one is y equals 1/3 to the power of x, and the top one is y equals 2 to the power of x. So reflection of the bottom one comes from -3, and it goes to close to the line y equals -2. So that's the reflection here. And the other one would go up. So this is the line x equals 1. And the other one would become something like this. So this is the reflection. And then we get a shape like this. This is going to be the rotation about the line 1. Okay, so we are going to evaluate the volume of this solid. So how do we find the volume of the solid? We can use the cross-section method and find the inner radius and the outer radius. So let's look at the inner radius. So what is the inner radius? The inner radius would be the distance from, let me use a different color, from here to here. This is the inner radius. This is the inner radius, and that is the bottom function plus 1. So that's 1/3 to the x plus 1. That's the inner radius. The outer radius is this distance right here. So the outer radius is 2 to the power of x and plus 1. The top function, and then plus 1 because it's all the way to -1. So these are the radii. So that means the cross-section area is going to be pi times the outer radius, so 2 to the power of x plus 1 squared minus the inner radius squared. So that's the area, which is pi times, we're going to square that, so that would be 2 to the 2x plus 2 times 2 to the x times 1 plus 1 minus 1/3 to the 2x minus 2 times 1/3 to the x minus 1. So I'm using the perfect square formula. So this would be pi times 2 to the 2x is 4 to the x plus 2 times 2 to the x. The ones cancel. So we get minus 1/9 to the x minus 2 times 1/3 to the x. So that tells us the volume is, we have to integrate these cross-sectional areas. Well, we know that the limits of x are from 0 to 1, so we have to integrate from 0 to 1, pi times 4 to the x plus 2 times 2 to the x minus 1/9 to the x minus 2 times 1/3 to the x dx. Now we know the integral of a to the x. The integral of a to the x is a to the x over natural log of a. So we're going to go ahead and evaluate that. So we get 4 to the x over natural log of 4 plus 2 to the x over natural log of 2 minus 1/9 to the x over natural log of 1/9 minus 2 1/3 to the x over natural log of 1/3 from 0 to 1. Now let's evaluate and simplify. So we can plug in 1, we get 4 over natural log of 4. Natural log of 4 is 2 natural log of 2 because natural log of 4 is natural log of 2 squared, and we can bring the exponent to the front. Plus 2 times 2 to the first, so 2 divided by natural log of 2 minus 1/9 over, so the bottom is 3 to the negative 2. So that would be minus 2 natural log of 3, and then minus 2 times 1/3 divided by, and the bottom is minus natural log of 3. So this part is the part that x is 1. Now we have to subtract, plug in 0 for x. We get 1 over 2 natural log of 2 minus 2 over natural log of 2 plus 1 over negative 2 natural log of 3, and then plus 2 over negative natural log of 3. So that is the answer. Now this does simplify. If you take the common denominator, you'd be able to simplify these. So you can take these 4, they all have natural log of 2 at the bottom, and we can simplify them. And then we can take these and we can simplify them. But I'll leave that to you to do the simplification. So this would be our answer. So to summarize, recall that we can use the change of base formula to evaluate integrals and derivatives. Derivative of a to the power of x is a to the power of x natural log of a, and integral of a to the power of x is a to the power of x divided by natural log of a. And that brings me to the end of this video. So I will see you in the next video.